What a pleasure to welcome back one of our favorite skyscraper members, John Briggs, who is really the guru when it comes to instruments of antiquity and not so much of antiquity. His favorite topic, one of his favorite topics has been George Ellery Hale, who has a large, well-known telescope named after him. And John is going to pursue this fellow's inventions in dealing with solar astronomy. And so please help me extend all the way to New Mexico, a warm skyscraper welcome to John Briggs.
Hi there.
It's great to be with you at Astro Assembly in 2022. I wish I could be there in real life, but I'm, of course, coming in virtually from Magdalena, New Mexico. And it's John Briggs speaking on noble instruments, Hale's solar telescopes, and his early vision for the solar-stellar connection. The first thing I want to do is acknowledge with gratitude how Seagrave Memorial Observatory has been a very important part of my astronomical life from my earliest interests in astronomy. My father and I were driving by on the main road near Seagrave back, it must have been about 1971. There was a sign at that time, Seagrave Observatory. We drove up towards it. We found Peatone Road, and somehow we just discovered Seagrave. Nobody was there, but we admired the building, and I never forgot about it. And as soon as I became old enough to get involved, I started attending programs at Seagrave, like just the monthly meetings and Astro Assembly, and I continue to be a member to this day, and I'm very, very grateful for everything that has happened there for me. Okay, well, here's a site that's going to be familiar to almost everybody there, the Stellafane Clubhouse up in Vermont, and how so many of us, probably nearly all of us, enjoy the Stellafane convention every summer. Now, if you go inside the front door there and turn to the right, there is a picture on the wall. It is among many, many other wonderful things on display inside the clubhouse there. Here's the picture I'm talking about. I think it's unlabeled, but it shows an elderly fellow, evidently observing the sun with some sort of apparatus. Well, this is George Ellery Hale, the subject of our presentation today. Hale was a heroic figure in the history of American astronomy, and I'm so grateful I've learned about him. He wrote quite a number of lovely popular books like these that folks have forgotten, but you can still find them via eBay, a book finder, places like that. They are well worth knowing about. I can't describe them all in this presentation, but his publications like these are really part of my inspiration for wanting to present to you today. There is one in particular that I want to highlight. It's thicker and heavier than any of the other books that he produced. Here's the title page, The Study of Stellar Evolution, an account of some recent methods of astrophysical research, 1909 by George Ellery Hale. It sounds a little heavy, doesn't it? But don't always judge a book by its cover. I think everybody hearing the presentation today would be fascinated to thumb through a copy of this book. You'll notice very fast that some 2/5 of the book are plates, illustrations, cool photographs like the 24-inch reflector at Yerkes Observatory, where Hale had been the founding director. A device called a spectroheliograph attached to Hale's personal 12-inch refractor. Alvin Graham Clark and Carl Lundin assembling the 40-inch objective at Yerkes Observatory in this classic, iconic photograph. The polishing of the 60-inch disc for the Mount Wilson reflector by George Ritchie, and always a chair or two in the field of view of the gigantic grinding machine to give a sense of human scale, even though in these photographs it seems almost never was a human being included. Mechanical parts of the 60-inch telescope being assembled at Mount Wilson in Pasadena, California. It goes on and on with instrumentation, including celestial photographs that were pioneering at the time in the early 20th century. Here, the spectroscopic laboratory on the summit of Mount Wilson out there in California. I mean, what cool instrumentation. And of course, illustrations of spectroscopic results that were so fascinating to Hale and his colleagues. Well, let's talk a little bit about how George Hale started as a kid interested in astronomy. It's incredibly interesting. George was a bright and precocious youngster and interested in all branches of science, including microscopy. And so there's a story about young George and microscopy that is especially poignant. He had experimented with simple microscopes. He aspired to get a better one. And he suggested this to his father. Now, his father was an elevator engineer in Chicago, profiting well after the Great Chicago Fire. Skyscrapers were going up, and they all needed elevators. Hale's dad was doing well financially, and George wanted a better microscope, and the wise father said to his son, "Look, if you will write it out for me and describe what you're going to do with it and why you really want it, if you put it in writing and do a good enough job of that, that I might consider getting you the microscope that you described." Well, that's what young George did, and the father, in fact, got him a new fantastic microscope. This really set the stage, it would seem, for Hale's ability to make proposals to sources of funding, to build the great telescopes of the 20th century, again and again over the course of his whole life. And in fact, he maintained an interest in amateur microscopy along with astronomy. And this instrument right here is one that he owned towards the end of his life in circa 1927, and he claimed that it was the income from some of those little books that I showed earlier that originally were magazine articles, issued again as books, but it was the mad money that George earned from his popular writing that he rationalized, allowed him to indulge himself in new microscopes at the end of his life, including this specific one right here. Now, the microscope anecdote was in the very early 1880s. And in a similar way, George wanted a telescope quite badly, and among his most significant early telescopes was a second-hand 4-inch refractor by Alvin Clark. That is, I guess his dad helped him get that too, but he got it in time for the 1882 transit of Venus. Now, George was born in 1868, so he was just a very young teenager, but still quite already in tune with astronomical happenings that he did not want to miss the transit of Venus in 1882. Now, around the same time as George recorded for us later, he had seen an article describing how to build a simple spectroscope. And in fact, he assembled one, and he fed it with sunlight, and he was just rapturous with the beauty of the solar spectrum and the mysteries of the Fraunhofer lines that the instrument revealed. He was bright enough to recognize how spectroscopy was a new tool that could really unlock the mysteries of celestial objects. He did this by himself and with an instrument about as simple as illustrated here in a drawing, actually from a book by Charles Young, the pioneering American solar physicist at that time, who also became a particular inspiration to George Hale. Hale went off to college at Massachusetts Institute of Technology, and he graduated there. But interestingly, his senior thesis was based upon work that George did at Harvard College Observatory, illustrated here. It was a little unusual for a young student to get involved at Pickering's Harvard Observatory, but Hale persuaded the director, Edward Pickering, that he was a serious young man, and Hale, as a senior thesis, attempted to develop a new form of solar spectrograph, the spectroheliograph, that he had envisioned on his own. Other folks at the same time had similar ideas, and actually in the preparation of this talk, I came across something that Hale wrote that acknowledged that some of these technical ideas for the spectroheliograph had been pioneered by his mentor, Charles Young. Now, I can't resist taking as an aside, before we talk a little bit more about the advanced spectroscopic instruments that Hale developed, by pointing out and celebrating how Seagrave Observatory has a beautiful solar spectroscope made by John Browning, designed circa 1875. And here it is attached to the Seagrave refractor. The Seagrave instrument was designed to allow observations of solar prominences and other chromospheric activity, like this drawing by the famous astronomical artist and observer Cruvelo, who worked in the same era at Harvard College Observatory with a solar spectroscope very similar to the one at Seagrave. With great patient care and observational skill, it was, as I'm going to describe, it was possible in this era to observe prominences without waiting around for a total solar eclipse. Again, to dramatize how it was before Hale and his peers came along in solar physics, let's spend just a little time talking about solar spectroscopes like the one at Seagrave. I'm very lucky to have acquired one twin to the Seagrave instrument shown in this photograph. Even the wooden box for mine is twin to the Seagrave instrument. All of these made by John Browning. One difference is that mine survives with the original laboratory stand, although this instrument was built really specifically to be attached to a telescope. Now, in brief, the idea was to project an image of the sun on the entrance slit of the spectroscope. In other words, no eyepiece on the telescope, but let a bright image of the sun shine on the widely opened entrance slit. And this, I'm sorry for this picture's not so hot, but it's out of Charles Young's wonderful book, The Sun, published in the 1890s, that explains how to do this. Here's a nice crisp picture of a solar spectroscope that was used by the famous English observer Lockyer, another pioneer of early solar physics. But there down on the lower right, the silvery slit jaws where an image of the sun would be focused. Here's what the entrance slit looks like in my instrument, which is again twin to the one, or nearly twin to the one at Seagrave. There are threads facing us, slightly out of focus in this picture, where the instrument would screw into the focuser of a telescope. In other words, no eyepiece, but the sun would be focused right on the square metal surface there. And you notice there's a slit that's open, and it's open fairly wide. The dispersion of the collimated sunlight would be quite high, thanks to the use of prism after prism in a prism train like this. We don't have time to talk too much about the technical details, though it's fascinating. Here's the one we have in the collection out here, which is really twin to the one at Seagrave, but I thought I would share this with folks there because it illustrates how the laboratory stand that survives with this one fits into the box, and there are spots in the box there at Seagrave. A stand could be duplicated based upon this example to complete the outfit at Seagrave. Then I hope we can make that happen someday, because you have empty spots in your box to accommodate the stand. Charles Young at Shattuck Observatory at Dartmouth College had a similar multi-prism solar spectroscope. In his case, it was made by Alvin Clark and Sons, and I couldn't resist showing off a picture. The instrument survives in the museum up there at Dartmouth College, and it's pretty neat to go see these things. What was the result at the eyepiece? Well, according to a delineation by Charles Young, it was something like this. You're looking at the solar spectrum, and with high dispersion, so in other words, the spectrum is highly magnified, the hydrogen alpha absorption line is very wide in the solar spectrum, but if the limb of the sun is tangent to the entrance slit, the chromosphere and features in it, like prominences, are shining in emission. The red light of hydrogen alpha, they are glowing like the nebulae that they are. And so that chromospheric structure could be imaged right through the spectroscope in the image of the spectrum, and that's how Young indicated it might look. And from studies like these, rotating the entrance slit around the limb of the sun, you could build up a picture of the chromospheric structure from day to, at any given time. And here's how Young drew the assembled results, making it look kind of easy, like Trouvelot's drawings also just kind of made it look easy. Well, I've done it myself to some degree, using the SNO solar telescope at Mount Wilson. And I recorded a picture to prove it. So that is the wide hydrogen alpha absorption line. Of course, there are many other absorption lines in the solar spectrum there. Very, very high dispersion, the spectrum extending widely to the right and left, but curious structure inside the red absorption line. Those are prominences. Chromospheric structure, because I wasn't looking at the disk of the sun, I was looking at the area of the sky just outside the limb, and sure enough, it works. Well, especially because you have this rare solar spectroscope there at Seagrave. I could not resist reviewing so briefly how it was designed to be used and what could be seen with it. But this really set the stage for the kinds of solar observations that were typical when Hale was an undergraduate in Cambridge, Massachusetts, but he had the audacity to aspire to envision better ways to do it. And thus he envisioned a more elaborate spectroscope, actually spectrograph, and he attempted to make it work there at Harvard College Observatory. It didn't really work, but it was good enough to serve as his senior thesis, but he knew he would simply go home and keep working on it because his father was encouraging him along in these researches. So, in fact, more or less as soon as George got home from college, in 1891, he was able to dedicate Kenwood Observatory in his backyard. This was Hale's backyard observatory, and it was sometimes described as Kenwood Astrophysical Observatory. Hale was so taken with the potential of applying spectroscopy to the sky and understanding things more clearly than ever physically, he really liked to emphasize astrophysics as opposed to the older astronomy, the astronomy of position and motion, as opposed to the spectroscopic analysis that he realized would prove so important in coming days. I've been told by a friend that this picture shows Hale at Kenwood Observatory in those early times. Again, it was dedicated in 1891. And to have such a facility as a backyard observatory was really quite extraordinary. But her family was wealthy, and father really did support his son's interest in these things. The instrument at Kenwood Observatory was as grand as the building. It was a 12-inch refractor with a lens by John Brashear, just like the one at Ladd Observatory there in Providence. But this Kenwood was mounted by Warner and Swasey. The telescope was equipped with a more advanced spectroheliograph, built again by John Brashear. This was executed with more time and effort and expense than what Hale had been able to devise as an undergraduate at Harvard College Observatory, and the example at Kenwood worked. And in fact, when the observatory was dedicated, Charles Young was the featured speaker. In 1891, Hale understood good public relations and all those kinds of political factors were worthwhile and important. And so the world knew what young George Hale was trying to do. And furthermore, he was succeeding. And he was able to photograph the sun in monochromatic light, in using not necessarily the red of hydrogen alpha, but the near ultraviolet, the extreme blue of calcium in the H and K Fraunhofer absorption lines. Why was he working in the blue to image the sun? Well, the photographic plates in that era were most sensitive to blue light. Solar astronomers around the world were becoming aware of the progress that Hale and the team of young scientists that he assembled right there at Kenwood Observatory were accomplishing in solar astronomy. And so it was only natural that people at the new University of Chicago were also aware of Kenwood Observatory. And to make a long story short, while Kenwood was dedicated in 1891, Yerkes Observatory, shown here, was dedicated only 6 years later. The lifetime of Kenwood in the backyard was really quite short because of the 3 domes you see here at Yerkes Observatory. The little one in the center is actually the same dome that Hale had in his backyard, because University of Chicago collaborated with Hale to create this Yerkes Observatory in 1897, and the Kenwood equipment and dome and instrumentation were woven right into Yerkes, and George Hale found himself as a young man director of mighty Yerkes Observatory. An amazing thing to have happened so fast. Because I have the ability to do so, I cannot resist digressing to show you a few contemporary photographs of surviving artifacts from Kenwood Observatory, from Hale and Kenwood Observatory in Yerkes. This is the Kenwood objective. When I had a chance to take it apart, one of the elements, the flint element, is chipped. It had been in storage for decades in a vault at Yerkes Observatory, and it was about, almost exactly 100 years after the dedication of Kenwood that I had a chance to take it out of the vault, disassemble it. Naturally enough, I found that it had been assembled backwards in its cell by someone in more recent times than when Hale used it. The thing is that Hale had 2 separate 12-inch objectives for his telescope, and here they both are. It's the visual one on the left and the photographic one on the right. Both Brashear objectives, but with the optical designs slightly modified, so the one on the right, photographic, will focus most sharply the colors in the blue region of the spectrum. The visual lens on the left would focus most sharply in the yellow-green, the part of the spectrum the human eye is most sensitive to. How do you tell the difference? Well, one of them is stamped on the cell visual, right there. And the other one is stamped photo, right there. Further, I can't resist saying something about the current status of the Kenwood hardware, the equatorial mounting. This is the south building, or once known as the laboratory building on the grounds of Yerkes Observatory, a couple 100 feet south of the historic building. In the south dome of the laboratory building, you walk underneath it, and there is a very significant pillar with an observing floor up the ladder. And inside the dome room, the equatorial head of the Kenwood refractor. It's neglected now, unfortunately, but at least it survives. And since the time this laboratory was built, I guess circa 1960, the Kenwood mounting has carried a Schmidt camera with a 16-inch primary mirror that was built, as I understand, right in the Yerkes Observatory shops. The original tube assembly to the Kenwood refractor is in storage, fortunately, surviving under the floor of the 40-inch refractor. But what confuses the issue a little bit are multiple sections survive because the original Warner and Swayze, as Hale knew it best, was a single tube painted with dark paint on the left, but in the late 1920s, the telescope was re-engineered with two tubes, like a double-barreled shotgun, by the Vleck company, and those sections are on the right in this cluster, painted with a lighter gray paint. Here's the center casting in aluminum for the re-engineered tube as it was done by Vleck for the double-barreled shotgun effect. So the center casting would be on the declination axle, and altogether 4 long tube sections would attach to it. Unfortunately, the original cast iron center section for the single-barreled original tube does not survive. The magnificent brass focuser to the Kenwood telescope with a bayonet mount to facilitate its removal for mounting plate cameras, the spectroheliograph, and other instruments like filar micrometers. This beautiful artifact is on display right now in the Yerkes Library reading room. And of course, there is a dream that the Kenwood telescope can be restored, put back together someday. But returning to the early spectroheliograph, what of it? Of course, Hale was perpetually modifying things and improving things. I believe this classic drawing of it shows it as Brashear supplied it in its original form to Hale. But having lived and worked at Yerkes, and having always been very interested in these things, I fear that what you see right here is all that now survives of the Kenwood spectroheliograph. And I didn't even know about this fragment until several years ago. But this is the plate holder and a moving slit. Without going into all the technical details of how a spectroheliograph worked, there are enough details shown in this photograph compared to other early, compared to early drawings and photographs of it, that I am convinced that this hardware really was part of the original instrument. So it's interesting just to contemplate the history of all this when we see it before us. But let's get back to the historical progression and these classic photographs showing the huge Yerkes refractor being assembled by technicians from the Warner and Swayze Company. The tube assembly coming together in the 90-foot dome. Some 63 feet long. What a job handling these massive parts before the conveniences we have of diesel-powered cranes, hoists, everything else. They're using block and tackle stuff, and of course, considerable experience and really good common sense. The fully assembled 40-inch refractor, dedicated 1897, and with its elevating floor at the top of its range. Notice inside the big glass aperture near the top of the pillar, just above the floor, the two gates in the gigantic flyball governor at the heart of the clock drive. The 40-inch objective with a tube pointed maybe some 20 degrees down, made by Alvin Clark and Sons in Cambridge, Massachusetts. An unusual contemporary photo by me of looking through the objective with my camera held in my hand inside the tube in an air vent, allowing the camera to be in the tube looking out through it at one of the dome rotation wheels. But as I've described before, and many of you have seen and heard, the commissioning of Yerkes Observatory was not without incident, was not totally smooth. The floor collapsed in this near tragic accident before the scheduled dedication. Nobody was hurt, but man, what an episode. Notice the observing ladder that still exists to this day. I've used that ladder down there at the bottom left. What a mess, and how stressful for Hale and everybody else involved with the observatory. They did not know for a while whether the vibration of this accident had damaged the lens, but it had not. But that was an episode, and there's more to be said about some of these problems, but they'll have to wait for another presentation someday. So even with the hiccups, Yerkes was dedicated and commissioned and was very successful, and it was kept busy, it would seem, day and night. Here with a stellar spectrograph attached to it. Here with a classic filar micrometer attached to it for measuring double stars and things of that nature. And here with the huge Rumford spectroheliograph, which was the next step in the evolution of solar spectroscopy as pushed forward by George Ellery Hale. And the young man that is said to be there taking the 10,000th glass plate spectroheliograph, or in other words, monochromatic image of the sun, was William Morgan. And William Morgan, after having been a student at Yerkes, continued as a staff member, and he did not pass away until 1994. And so I started at Yerkes in late 1990 as an engineer. So Morgan had become a very well-known stellar spectroscopist among other research interests, and at least I had a chance to know him, overlap with him, although he was getting so advanced, and he was ill, but yet still a presence at the observatory as my wife and I were there in the early 1990s. Now, if you look down from a bird's eye view on Yerkes Observatory, it looks like it has the shape of a Roman cross, with the long axis of the building having the 40-inch dome at the base of the cross, but then the arms of the cross have the two smaller domes. The arm pointing towards the north had the Kenwood dome and refractor, but near the Kenwood dome, in the roof, was a roll-off observatory, and that exposed part of a long room that Hale called the helioscope room. And the idea, as Hale envisioned from the conceptual design of the building, was to allow mirrors mounted here to capture sunlight and direct a sunbeam down this long attic corridor to allow very long focal length solar instruments for highly magnified views of the sun and for high dispersion solar spectroscopy. In this case, though, as we see it, they're testing some kind of Newtonian reflector. This might have been a prototype tube assembly for the Ritchie 24-inch, but I also know that folks at Yerkes experimented with an 18-inch caliber mirror that survives at Illinois Wesleyan University. So I wish I knew what this, exactly what this sort of Dobsonian-like telescope shows there in the roll-off roof of the heliostat room. But the point is that in the detailed conceptual design of Yerkes, Hale had envisioned a long rooftop solar observing laboratory, the heliostat room. Thing is, although some interesting science was done here, at nighttime science too, like infrared detection of Arcturus, things of that nature, it didn't work out so well because the seeing was terrible. The air turbulence, the sun baking down on that lion there, that gargoyle and everything else made a lot of air turbulence. So on very short order, Hale moved on to envision better ways to observe the sun. So in the basement Yerkes machine shop, large cast iron parts were built up to carry optics for a horizontal solar telescope. Hale likely had these concepts in mind for the heliostat room, but these parts never got all the way up there. And so Hale and his team built a simple wood-framed building on the south lawn. That's actually Lake Geneva in the distance, in the overexposure there. But a long building allowing a very long focus horizontal telescope and provision for high dispersion solar spectroscopy. And here are the mechanical parts, or at least some of them, exposed in the roll-off roof building. Now, it's interesting, I never really thought about it until just now, but the architecture of the building is allowing a morning view, but not an afternoon view. And that's because by now, Hale and his colleagues recognized that the atmosphere was overwhelmingly more stable in the early morning for viewing the sun than it ever was in the late afternoon. But notice the optics aren't installed yet. They have been installed, unfortunately, very soon afterwards, by the time this photograph was recorded. Another unfortunate early disaster for Hale and his solar program. Here you see the optics after the fire, but amazingly, the heavy mechanical parts, cast iron and steel, they generally survived. And obviously, it must have been a terrible drag to suffer that loss. But Hale and his team rebounded and simply began construction of an entirely new observatory, even more grand than the first one. And the telescope was renamed the Snow Telescope because a local wealthy lady, Helen Snow, provided the funding to name the telescope rebuilt, Phoenix-like, literally, after her father. And so they continued, hardly skipping a beat, even after such a serious setback. And here are the mechanical parts with new optics. That's a 30-inch optical flat in the lower mirror holder there, in a coelostat mounting to capture the sun and create a horizontal sunbeam as reflected off the upper optical flat. And this is in the wood frame replacement building. But it didn't last long here, interestingly. But I can't resist digressing yet again from the historical progression, because perhaps unfortunately, when University of Chicago decided to close Yerkes Observatory in the late 20-teens, they invited me back to do an inventory of the hardware still surviving there, and it was quite a task, but I did it. And it gave me a chance to go through more secret spots where interesting artifacts like this had been saved. From the edge, 2 3/8 inches thick, obviously part of a disc. Looks kind of optical, doesn't it? And there's a sticker on it. Part of mirror destroyed by fire in first horizontal coelostat telescope south of YO Yerkes Observatory, but it's the initials at the top of the tag EEB. This is the handwriting of Edward Emerson Barnard. Pretty cool. Barnard, of course, was another heroic early American astronomer, the discoverer of Amalthea, the fifth moon of Jupiter, at Lick Observatory. But Hale at Yerkes recruited Barnard away from Lick, and at Yerkes, Barnard traveled to Mount Wilson with an astrograph and recorded plates for his famous atlas, photographic atlas, like to reach the Milky Way. He was such a perfectionist, though, he couldn't finish the atlas before he died, and it was left to the Yerkes Observatory director, Frost, and Barnard's niece, Mary Calvert, to finish the atlas as co-authors. In any case, there's this slip of paper here, Mr. Kuiper. These paperweights are fragments of the Sealstadt mirror that was destroyed when the temporary Sealstadt building south of the observatory in the early days was burned. And MRC, those are the initials of Mary Calvert, the other a co-author of Barnard's famous Milky Way Atlas, which is a real collector's item nowadays. Well, back to the historical progression. Things were happening fast at Yerkes, but probably never fast enough for energetic and driven George Hale. And so here he is, peering out from the summit of Mount Wilson in California. Hale had begun to recognize that sites out west, like Mount Wilson, were tempting alternatives from rural Wisconsin for astronomical observing. Hale was looking over a view like this west towards the Los Angeles basin and beyond it, the Pacific Ocean, not so terribly far beyond it, but when this photograph was taken, the so-called marine layer had engulfed the valley, the point being the observing conditions at nearly 6,000 feet on the summit of Mount Wilson above Pasadena, they could be spectacular. Now, in terms of steady air, high resolution observing, and of course in the beginning, it was still quite dark at Mount Wilson as well. Harvard College Observatory had come out in the late 1880s, and they had wintered over at the site with a refracting telescope, but the winter conditions proved quite severe. So that expedition was not encouraging. But Hale reinvestigated Mount Wilson and found the site quite compelling. They say that Hale climbed a big pine tree carrying a 4-inch refractor or some such instrument to get a daytime view of the sun with a white light filter to confirm that with that a little bit of additional elevation to be above the ground layer turbulence, the steadiness of the air could allow spectacular high-resolution views of the sun like this. And he confirmed it, and thus the Yerkes Observatory expedition to Mount Wilson began. The early volumes of the Astrophysical Journal are still very readable, in my opinion, even for non-specialists. And you can see illustrations like this, of all places, in the APJ, Astrophysical Journal, and it's the heart of the snow telescope, the Sealstadt mounting, being pulled up the mountain by this poor horse with the special wagon. The guy in the back steers the rear wheels because the trail was so narrow and primitive, but I can tell by looking at what's on that cart there, that is actually the polar axle stand to the snow heliostat mechanism. Again, phoenix-like from that fire. It came out on loan from the new observatory after hardly been installed in the new observatory at Yerkes very long. Hale and his team shipped it to the Mount Wilson summit for this expedition. And yet another housing for the snow telescope was constructed right near the precipitous edge, highly elevated because folks had begun to recognize that for every foot you can get above the ground, the air turbulence lessens and the images, especially solar images, were sharper. So great effort was put into taking advantage of the best air. Here's one end of the huge snow enclosure, housing the coelostat with the roll-off structure. So the flat mirrors can capture the sunbeam and create a horizontal sunbeam, or nearly horizontal, extending down to the lower right. Let's look at some relatively contemporary shots of the snow that I took. Most of these would have been in the very early 1990s, when I was very fortunate to have a chance to help reactivate the snow for the first years of the Curia summer program that for decades ran on Mount Wilson for undergraduate students. It's been renamed this last summer, but the program really continues to this day. This shot shows the sun shining down towards a 30-inch optical flat in the large mirror holder closest to us. That's the coelostat. It tracks the sky at half the sidereal rate, but consequently, the beam reflecting off that flat is stationary, and the second mirror on the upper left, that's not part of the coelostat, it's referred to as the second flat in setups like this. The second flat, which is about a 24-inch, redirects the beam more or less horizontally off to the right. Consequently, the beam can shoot down through the length of the snow building, and it's illuminating something in the far distance there. Let's go inside and take a look. This is the target. It's a 24-inch paraboloid with a 60-foot focal length, so it's f30. Check out the green glass. We're looking through the back of the mirror blank there, and it looks like we're looking through it and can see the corrugation on the wall, but no, it's illuminized. We're looking at the reflection of some metal corrugation in the green there. In any case, let's see what happens after the beam reflects off this concave mirror and, of course, begins to converge and focus an image of the sun. The beam converges from the paraboloid and is directed towards a smaller optical flat that is mounted on the ceiling of the building. And then finally, the beam comes down vertically, and there's a piece of black cloth that's creating smoke in the f30 focus of the telescope, just to help dramatize this image. It really shouldn't allow much smoke in a situation like this, but the image is nice. In any case, there's a 6 or 7 inch diameter image of the sun being created in the prime focus of that f30 24-inch paraboloid, and it's being created on the top of the white mechanism, which is the top of a massive solar spectrograph. The image of the sun is entering the spectrograph, which is in a pit dug down into the mountain, some 30 or 35 feet. And these two folks were students in the very first year of the Curia program. That's Consortium for Undergraduate Research and Education in Astronomy, which was led by Joe Snyder of Oberlin College. But I was very fortunate to be on the staff there in the very early days of this. And my friend Perry Rose, who continued on in astronomy, is looking at the spectrum that is coming back up out of the spectrograph, a lithro-type a spectrograph in an aperture that's under his face there, and he has to be a little careful lest his hair catch on fire from the sunbeam right outside his body. And here I am, not too long afterwards, but it's already over 20 years ago, with my son Nicholas visiting the snow, and in front of my bare leg is a horizontal aluminum disc and painted white, and that is actually the solar image. The disc has been swung to capture the image of the sun. Right underneath that disc is the entrance slit to the solar spectrograph, which can be used as a spectroscope. Notice that just in front of Nicholas's foot hanging down, there's a 2-inch Teleview Plossel eyepiece, 55 millimeter, it's sitting in a 2 by 10 inch plate holder. That's where you would record a spectrum of the sun on a 2 by 10 inch glass photographic plate, but you could view the spectrum in beautiful, beautiful detail through the snow spectroscope. You could use it as a spectrograph, but you could use it as a spectroscope, just putting an eyepiece where glass plate would normally be held. And the beauty of the solar spectrum is really something to talk about. Not far away from where I was standing with my son, there's a hatch on the floor, and there's a ladder that goes down into the pit where the optical elements of the Litro spectrograph are housed. The entire body of the spectrograph mechanism can pivot in a vertical axis that facilitates sweeping the entrance slit, say, around the limb of the sun, just the way observers like Trouvelot did it back at Harvard College Observatory, or otherwise angling the entrance slit however one might want to do it relative to the disk of the sun. On talking about the technicalities, it's really cool having a chance to see the stuff firsthand and spend time understanding it and appreciate the insight of the people who put this all together. At the heart of the Litro spectrograph, there's a diffraction grating that had been ruled in the grating laboratory of Mount Wilson Observatory, their headquarters down at Santa Barbara Street in Pasadena. The blank is an optical flat about 6 inches in diameter, and the optics, imaging optics of the spectrograph are in the brass tube extending out of focus above in the picture, but we just don't have time to get into all the details, but they're cool. But as soon as Hale had the snow up and running, he was visualizing, yet again, better ways to do it. Here's a schematic drawing of what came to be the 60-foot tower telescope, where again, there is a spectrographic pit going down into the mountain that has the advantage of temperature stabilization too. But in this case, the reflecting elements to capture the sunbeam are at the top of a tower, and the imaging element is a 12-inch diameter lens up there at the top of the tower, also with a 60-foot focal length. By the time the 60-foot tower became a reality, Hale had created Mount Wilson Solar Observatory with its own funding from the Carnegie Institution. And so he left Yerkes Observatory of University of Chicago. Collaboration was still very close, but the conditions at Mount Wilson were just too compelling, and the funding was excellent, and the opportunities were very stimulating. Here's a later view of the 60-foot solar tower, where basically a second tower had been built around the first. The inner tower holds the optical elements. The outer separate structure holds the dome that would help minimize wind shake on the optical parts and the inner tower. And let's see, as I've said, Yerkes was dedicated in 1897, and if I remember correctly, it was only 1909, or very close to that, when Hale, using the 60-foot solar tower here, made his really great discovery. So all this had happened in only a decade or so after the dedication of Yerkes Observatory. He was already out here in California making arguably his greatest discovery. I mean, how dizzying. What a pace for him and his team. Here is the head of the spectrograph at ground level of the 60-foot tower. Very similar to the instrument that was at the snow telescope. And here is Hale standing beside it. So what was his greatest discovery? It was by looking at the spectrum, particularly of sunspots. Hale recognized that the spectra of sunspots changed. The Fraunhofer absorption lines were oddly widened and doubled and occasionally tripled in an effect that had been recognized in laboratories called the Zeeman splitting. If a light source was subjected to very, very strong magnetic fields, the light source in emission or absorption would display a spectral change, a doubling or splitting of the associated absorption line. And Hale saw this in the spectrum of the sun. Here's an image of it. So there's a big sunspot on the left, and the dark vertical line represents the entrance slit of a spectrograph. The image on the right is in very high dispersion Fraunhofer absorption lines. There are horizontal streaks that are dark because there's not so much light in the spectrum there, because we are looking at the dark light of the sunspot. But also centered in the spectral view, a line is puzzlingly split into three components, also right in the core of that sunspot. That was the Zeeman splitting, recognized from laboratory experiments, but now observed in the sun. It proved that very strong magnetic fields were associated with sunspots. That was astrophysics, and then some, and was a very important step forward in understanding the physical nature of the sun. Wouldn't you think that would have been enough? But of course, Hale simply envisioned yet better ways to make more observations, to understand things in more detail. So they began building a 150-foot solar tower to get even better, sharper views. Look at the man at the top of this structure under assembly. the completed 150-foot solar tower. Notice the fellow on the ladder halfway up on the left-hand side. And a view at the top of the tower, a friend to many of us, Larry Webster, who was for many years the chief solar observer. More recently, the site manager for the Georgia State Interferometer on Mount Wilson. Larry, now in retirement, is still in residence at Mount Wilson and is a very dear friend. Other people would occasionally visit the top of the 150-foot solar tower. I leave it to you if you can recognize any of these three, perhaps particularly the fellow with the wild hair on the right there. A schematic of the overall layout. I've gone on a long time. I've got to wrap this up, so I'm going to kind of skip it, but it's the technical details are so interesting. A close-up of the top. Maybe you can pause the YouTube and look at it if you care to. A close-up of the bottom, dramatizing how, in the case of the 150-foot tower, the spectrographic pit goes down to a depth of over 75 feet. Too much has been accomplished with these solar instruments for me to even begin to try to explain my limited familiarity with all the progress made with them. But to this day, sunspot drawings are still done with a 150-foot tower. It produces an image of the sun about 17 inches in diameter. And this is kind of a close-up. I think this is a drawing by Larry Webster. With the instrumentation there, they can also identify the magnetic fields, the north and south, associated with the spot phenomena. No polarities were recorded on this day, it says, because due to a lack of time. The sunspot drawings now are actually done by retired volunteers, as I understand, at Mount Wilson, but they are still continuing. Hale was well aware of Russell Porter and the American amateur telescope making movement in the late 1920s and 1930s. And Hale recruited Russell Porter, the founder of Stellafane, to come out to California and help in the design and the general conception of the 200-inch project, among other things. So there was an intimate relationship between Hale and Porter in their later years. Hale envisioned that a relatively simple form of spectrohelioscope could be built by amateurs, but his vision was that if the sun could be monitored in hydrogen alpha light in a worldwide network, it could be better establish the amazing relationship between solar flares, which can be so dramatic in hydrogen alpha, and electromagnetic disturbances on Earth involving huge auroral storms, events like the Carrington event in 1859. This had really yet to be absolutely established. The sun-Earth connection, with complete confidence. Hale believed that a network of spectrohelioscopes, as shown here in a drawing by Russell Porter in the famous ATM, amateur telescope making volume that many of us are so familiar with. Well, this was an important thing to advocate, and the story is so long I can't, of course, but touch upon it here, but very interesting stuff. And there was an example of one of these instruments begun at Stolfane, and very fortunately, thanks in recent years to Matt Considine, they got a more complete Hale spectrohelioscope resurrected and with a team housed and put into operation at Stolfane, and that is a major feature of Stolfane today, right beside the famous Pink Clubhouse. And I leave it to you to visit there to learn more about it. It's really cool. Mount Wilson went on to see the 60-inch finished, considered the ancestor of all modern observatory reflectors, and of course the 100-inch reflector in less than a decade later. Hale was manic depressive, you might say.
Hey, this is, I saw the chat. I may have somehow stopped the voice, but can you folks hear me?
Yes.
Yes.
Good. Okay. Well, the hell with the pre-recording. We're right near the end. Thank you for your patience. But so of course the 100-inch came online. Now let's see if I can advance it. I shouldn't have hit chat. Oh, here we go.
Suffered a serious and debilitating mental illness that makes his story all the more amazing. How he was able to accomplish so much with the mental difficulties he had that one can only imagine related to his hard-driven aspirations and the stress that he endured, desiring these things so strongly. Not so long after the 100-inch was commissioned in 1917, Hale had to assume the role of honorary director of Mount Wilson because his mental health really didn't allow him to continue in the same way up at the mountain site. But nevertheless, down in Pasadena, he built his own new backyard observatory. He didn't actually live right on the grounds of the Hale Solar Laboratory, but he could easily commute to it. It happens to be very close to the Caltech campus. The front door with Egyptian style art, dramatizing it, solar rays, shine down.
I tell you what, folks, I've cut it too close. I didn't realize the next speaker was coming on so soon. And I don't want to abuse you more than I have. I just wanted, with the final slides, to show off the amazing private observatory that Hale built that not so many people know about, the Hale Solar Lab. And I wanted to mention a little bit about how there were amazing stellar observations of stellar spot cycles using the 60-inch telescope that really dramatized the solar-stellar connection that Hale envisioned with the construction of all this stuff. And I think maybe I better just cut it off and thank you for your attention with my too long presentation. It's really hard to talk about Hale and everything he did, without being long-winded about it. But, so there, why don't I just stifle myself on that note? Thanks again for your attention, folks.
Well, that was excellent. And you delivered what we come to expect when you give a delivery. It's professional, it's thorough. And my only regret is we really don't have time for questions at this point. But just excellent. And I hope we get to see you here in the East sometime. And until then, we wish you well, safe travels. And again, thank you very much. There we go.
Thanks, folks. Wish I could be there. Here's my magic mirror, if you could see me. So, see you later.